Ever heard of a skyrmion? Sounds kind of like a Star Wars thing, right?
Yeah, it does, doesn't it?
But it's actually this crazy, tiny magnetic swirl, like a microscopic galaxy. But instead of stars, it's all about spins.
I like that, a tiny galaxy of spins.
Pretty cool.
Yeah.
But we're going even deeper today into this weird mirror world.
Oh, yeah.
Antiskyrmions.
The antiskyrmion.
We're talking some serious physics here, folks, with this paper, Simulating Magnetic Antiskyrmions on the Lattice. Good thing we've got expert speaker along for the ride, right? Help us wrap our heads around this stuff.
Absolutely. And you're right to call antiskyrmions weird. Scientists have been thinking about these things, like, theoretically for a while now.
Right.
But actually finding them in the real world, different story.
Yeah.
That's a challenge. This paper uses computer simulations to try and figure out why they're so elusive.
So before we go totally down the rabbit hole, let's
Yeah.
back up for a second.
Okay.
High school physics, right? Vaguely remember magnets, North Pole, South Pole. Like the ones on your fridge.
Exactly. The classic bar magnet, the dipole.
Right.
But hold on to your hats because it gets way more interesting with something called chiral magnets.
Chiral magnets.
Yeah. Instead of a simple structure, think of their atoms like a spiral staircase.
Okay.
And that inherent twist, that chirality, that's what leads to some really unexpected magnetic behavior, and that's where we find our skyrmions and our elusive antiskyrmions.
Okay, wait. So instead of a straight line, we've got atoms doing a spiral staircase thing.
Yeah.
And that, what, messes with the magnetic field?
It totally changes how the magnetic fields interact, yeah.
So it's like those staircases in old castles, you know?
Yeah.
The ones that only go up in one direction.
I like that analogy, yeah. It's all about how the structure influences the behavior.
Okay, so we got these weirdly structured magnets. But how do we go from a spiral staircase of atoms to like a swirling magnetic field? And what even makes a skyrmion different from an antiskyrmion? I mean, they sound like they should be like fighting each other in space or something.
Well, picture this. You've got a magnetic field, but it's pointing in every single direction at least once, and all within a tiny, tiny space.
Okay.
That's your skyrmion. Now imagine its mirror image flipped in a very specific way. That's your antiskyrmion. Technically, they have what we call opposite topological charge.
Topological charge.
Right.
What's-
Think of it like this. You've got a donut, right?
Sure.
You can squish it, stretch it, but it'll always have that hole in the middle. You'd have to tear it apart to get rid of that hole. That's kind of like topological protection. It means skyrmions and antiskyrmions are pretty stable. They don't just fall apart easily.
So skyrmions and antiskyrmions are like tiny little magnetic donuts.
In a way, yeah. But instead of dough, there were these swirling magnetic fields. And to make things even more interesting, antiskyrmions, they're like the rare elusive donuts, way harder to make.
Harder to find.
Harder to find, exactly. And that's what this paper is trying to figure out. Like, how do we even begin to find these things?
Right.
And that's where the simulation comes in.
So they built like a magnetic universe inside a computer.
Exactly. They created this virtual space called a lattice, and it's made up of spins. Think of it like a 3D grid where every point represents the magnetism of an atom. Then they program in all the forces involved, right? So you've got your typical ferromagnetic exchange,
Okay.
which is trying to make all the spins line up like little soldiers all in a row. But here's where it gets really cool. They also include this thing called the Dzyaloshinskii-Moriya interaction.
The Jell-O what? Say that 5 times fast.
Right. It's a mouthful. We'll just call it the DM interaction for short.
Okay.
And this DM interaction, that's where a spiral staircase, that chirality, that's where it really comes in. And to make things even more interesting, different types of DM interactions lead to different types of skyrmions.
It's like choosing your flavor of skyrmion.
Exactly.
So which flavor gives us antiskyrmions?
For antiskyrmions, we need a very specific type of DM interaction, one that's associated with what we call a D2D crystal structure, and that's exactly what the researchers were working with in this simulation.
Okay, so we've got this like virtual magnetic world set up, right?
Yeah.
With the right flavor to maybe make some antiskyrmions. But how do they even find these things in the simulation? Like, it's got to be more than just looking for tiny little swirling arrows on the screen, right?
You're right. It's a little more complicated than that. What they did is they used their simulation to make what's called a phase diagram.
Okay.
Think of it like a treasure map, but for antiskyrmions.
So X marks the spot. for antiskyrmions.
Yeah, exactly. The phase diagram tells you the conditions where these antiskyrmions are most likely to be stable. So it maps out things like temperature, magnetic field strength, and shows you like the sweet spots where these things might pop up.
Did they find the X?
They did. They found the X. But, and this is the tricky part, that sweet spot for antiskyrmions, it's really, really small.
Oh, no.
And very specific. You change the temperature, the magnetic field, even a tiny bit, and poof, they're gone.
So it's like trying to, find a snowflake that only exists at a very specific temperature.
Exactly.
And, hoping the wind doesn't blow it away.
Yeah, and to make things even more interesting, they found that these antiskyrmions could sometimes act like magnetic ghosts.
Magnetic ghosts. You're messing with me, right?
No, I'm serious. What I mean is, in the simulations, they found that sometimes these antiskyrmions would stick around even after the conditions changed, like a ghostly memory of their existence.
Okay.
And that's a real phenomenon. It's called hysteresis.
Hysteresis. Okay. I feel like I've heard that word before, but give me a real-world example. Give me an analogy. I'm all about analogies today.
Okay, think about a light switch,
Okay.
but it's a little bit sticky.
Okay.
So you have to flick it past the on position to get the light to actually turn on.
Right, right.
And then maybe even flick it a little bit further back to get it to turn fully off.
Yeah, yeah.
That's hysteresis.
Okay, so you're saying these things are like, we were here, we might still be here.
That's a great way to put it. And what's really cool is this hysteresis effect. They've actually seen this in real experiments, not just in the simulations.
Oh, wow.
So it's a real thing.
So we're talking about tiny magnetic swirls that hold a grudge? That's pretty badass.
Yeah.
But did the simulation tell us anything about how these things appear and disappear in the first place? Is it magic? They just sort of blink in and out of existence?
Well, they actually simulated the birth and death of these antiskyrmions. And it's even wilder than you might expect.
Okay.
It involves something called a block point.
A block point. Okay.
Yeah.
What in the world is a block point?
So you know how magnets always have a north pole and a south pole?
Right.
A block point is kind of like finding a magnetic monolith, like a single pole all by itself.
Okay.
Which is normally impossible, right?
Right.
It would be like finding a north pole without a south pole.
I'm a magnetic unicorn. That's nuts.
Right. And in the simulation, they found that these block points act like unravelers. So when a block point gets involved, the antiskyrmion can basically disappear.
So these tiny little anomalies, these magnetic unicorns, they can control these magnetic swirls.
Potentially, yes.
That's insane. What are the implications of that?
If we can understand these block points and how to control them, then we might be able to control the formation, the destruction of antiskyrmions, and that has huge implications for all sorts of technologies.
Okay, my mind is officially blown. This is way cooler than any of those boring bar magnets I learned about in school. What else did these, simulation wizards uncover?
Well, they found something else that's really crucial if we ever want to actually control these things in real life. Size matters.
Okay, that's usually what they say, but what does that mean in this case?
In this case, it means that the strength of that twisting DM interaction we talked about, remember the spiral staircase?
Right.
That directly impacts how big these antiskyrmions can get.
So if you tweak that DM interaction, you could have a whole range of antiskyrmion sizes.
Yeah.
From tiny little swirls to giant magnetic hurricanes.
Exactly. And that's a big deal because it gives scientists a potential way to control not just whether an antiskyrmion forms, but also its size.
This could be really useful for, everything. I'm telling you what, this is some mind-blowing stuff. We zoomed down to the nanoscale and found this whole other universe of magnetic forces and possibilities, really.
It really makes you think. You know?
Yeah.
What else is hiding in these research papers just waiting for us to uncover it?
Exactly. But for those of us who aren't out here simulating magnetic universes every day, what does it all mean? We've got these simulated antiskyrmions. We know a little bit about how they behave, but what's the big takeaway? Why should we even care about these tiny magnetic swirls?
Well, first off, it tells us that antiskyrmions aren't just some theoretical possibility. They could be real.
Yeah.
Actually out there in the real world, hiding in the right materials. This simulation gives us a place to start looking.
So we need to go through lists of materials, right? Looking for that special D2D crystal structure, the right temperature, the right magnetic field. It's like a microscopic scavenger hunt.
Yeah, like a scavenger hunt for magnetic unicorns.
Wow.
And once we find the right materials, then things get really interesting. Imagine actually being able to create these things in a lab, controlling these tiny little swirls of magnetism.
So this could be the future of data storage. Like some kind of crazy new computer technology.
It could be. I mean, they're incredibly stable.
Right.
They're tiny,
Yeah.
and they're potentially very, very fast.
Right.
We could be talking about a total revolution in how we store and process information, and the fact that we can control their size, control their behavior using things like that DM interaction. That opens up the door for some really wild stuff, like neuromorphic computing, where you're trying to mimic the human brain.
Wow.
We're talking about computers that are not just faster, but way more efficient, more powerful than anything we have today.
This has been an amazing deep dive. I had no idea something so small could be so complex, so potentially world-changing.
It really is amazing, isn't it? The power of scientific curiosity. Sometimes the most groundbreaking discoveries come from the most unexpected places.
Well said, well said. And on that note, we'll leave you to ponder the mysteries of the magnetic universe. Until next time, keep those brains buzzing.